Hi, my name is Dr. Bret Bennington. I'm a professor in the Department of Geology, Environment, and Sustainability. And I'd like to talk to you a little bit today about climate change um, as it relates to the common reading book, Greta Thunberg's No One is Too Small to Make a Difference. So what I want to do today is just review the basic science behind climate change, which I think will be helpful for understanding Greta's speeches and the arguments that she makes. So we're going to take a very quick look at what are the factors that control Earth's climate, how are humans impacting those factors, what are the consequences of a changing climate, and why is it a problem? For any planet orbiting a star, the habitability of the planet depends a lot on the distance of the planet to the star. So planets need to be within a region where they receive enough energy from the star, enough heat, so that liquid water is capable of existing. And that kind of sets the conditions for life. There are 3 planets that are potentially within the habitable zone in terms of their distance from the sun: Venus, Earth, and Mars. Now, Venus is way too hot. It's hellishly hot with an average surface temperature of 864 degrees Fahrenheit. So even though it's in the habitable zone, it's not a habitable planet. Mars, which is also within the habitable zone, has a very cold surface temperature, an average of minus 67 degrees Fahrenheit. So it's not habitable, whereas the Earth is the Goldilocks planet. It has the perfect conditions for life. Now, all 3 of these planets are in the habitable zone, but only the Earth is habitable. What's the deciding factor? Well, the deciding factor is the atmosphere. What really controls a planet's climate is the composition of its atmosphere. And the problem that Venus has is that it has too much carbon dioxide in its atmosphere. And the problem that Mars has is its atmosphere is too thin, so it has too little carbon dioxide. The Earth has a small amount of carbon dioxide in its atmosphere, less than 1%, but it's just the right amount to keep the planet warm. Now, how does this work? Well, the physics are very well understood. Light coming from the sun, most of the energy coming from the sun, in fact, is coming in the form of visible light. Visible light passes through the atmosphere of the Earth very easily because almost all of the gases that make up the atmosphere of the Earth are transparent to visible light. The light strikes the surface of the Earth, the surface heats up, and that energy is converted into a different wavelength. It's converted into heat energy in infrared wavelengths, and that energy tries to escape back into space. It's radiated back through the atmosphere, and it would travel through the atmosphere and go back into outer space if not for the presence of certain gases in the atmosphere, particularly in the lower atmosphere, where most of the atmosphere is, that are able to absorb that heat energy and re-radiate it back towards the surface. We call these gases greenhouse gases because they are capable of heating the surface of the Earth in much the same way that the glass around a greenhouse keeps the air inside the greenhouse warm. And we need greenhouse gases. If the Earth had no greenhouse gases in its atmosphere, then energy would come in, the surface of the Earth would heat up, that energy would be radiated back into space, and that would cause the Earth to be a frozen snowball with an average surface temperature of about minus 18 degrees Celsius. The oceans would freeze solid, and we would not have a biosphere. With a relatively small amount of greenhouse gas, the Earth is a much warmer planet. And the reason, again, is because these greenhouse gases are capable of trapping heat that's being radiated off of the surface of the Earth and keeping that heat within the lower part of the atmosphere and warming the atmosphere near the surface of the Earth. And that gives the Earth an average surface temperature of around 14 degrees Celsius, which is perfect conditions for life. Now, it turns out that there are several gases that function as greenhouse gases, but the most important greenhouse gas, for a number of reasons, is carbon dioxide. And carbon dioxide is a gas that's continuously entering and leaving the atmosphere at different timescales. But for the purposes of understanding climate, at least climate as it unfolds over human timescales, The most important factor affecting the amount of carbon dioxide in the atmosphere is photosynthesis. So plants absorb carbon dioxide, grow, and convert the carbon in the carbon dioxide into organic carbon in the plants. And when plants die, that organic carbon is oxidized either through cellular respiration in plants and animals, or combustion or burning of plant material, or decay processes, which collectively put the carbon dioxide back into the atmosphere that was removed by photosynthesis. However, over hundreds of millions of years, some of the organic carbon produced by photosynthesis has been buried in the crust of the Earth. And when you bury organic carbon in the crust of the Earth, it doesn't reunite with oxygen, and it doesn't get back into the atmosphere. So for roughly 300 million years, the Earth has been storing away organic carbon in its crust. And that organic carbon is what forms fossil fuel deposits. When we extract fossil fuel from the crust of the Earth and burn it, we take that carbon, which has been stored away for, again, hundreds of millions of years, and we put it back into the atmosphere. So fossil fuels are sedimentary deposits of organic carbon, whether you're talking about oil, natural gas, or coal. This is carbon produced by photosynthesis over hundreds of millions of years, which includes high energy bonds between the molecules in the organic carbon. We dig up these fossil fuels, we burn them, we release the energy to power our civilization, and the carbon goes back into the atmosphere. And we've been using fossil fuels now for about 150 years, actually longer than that, but our use of fossil fuels really started to take off when we were well into the Industrial Revolution, and after World War II, fossil fuel consumption really began to increase exponentially, and to the point where nowadays we are releasing something on the order of 6.5 to 7 petagrams of carbon into the atmosphere every year in the form of carbon dioxide. And we've been measuring carbon dioxide levels in the atmosphere since the late 1950s. And we can see the steady rise of carbon dioxide in the atmosphere. Back in the late 50s, carbon dioxide levels were below 320 parts per million. And as of April of this year, carbon dioxide levels were at 416 parts per million. So there's a steady increase in carbon dioxide in the Earth's atmosphere, which is directly related to human activities, mostly the burning of fossil fuels. There are other things that we do that release carbon dioxide into the atmosphere, but burning fossil fuels is the main one. How do we know what the impact of the carbon dioxide is that we're adding to the atmosphere? Well, geologists are capable of studying the composition of the atmosphere going back into the past several 100,000 years, because we can drill down into glaciers, particularly the thick ice sheets over Antarctica and Greenland, extract these cores of ice, and trapped within the layers of ice in these ice cores are little bubbles of atmosphere that formed in the ice as the ice accumulated going back into the past. So we can extract a record of the composition of the atmosphere going back, well, about 800,000 years. And from the trapped gases in these bubbles, we can measure the composition of carbon dioxide in the Earth's atmosphere. And from the oxygen in the gases and in the ice, we can estimate the temperature. We can see temperature changes as well. And what we've been able to work out is that the amount of carbon dioxide, the main greenhouse gas in the Earth's atmosphere, has fluctuated quite a bit over the last 400,000 years. It has fluctuated between values of around 175 parts per million and values up around 300 parts per million. And when carbon dioxide levels are high, the Earth's climate is warm. These are the interglacial periods. And when carbon dioxide levels are low, it corresponds with the major ice ages that have occurred. So we have a warm interval, a glacial interval, a warm interval, glacial interval. So carbon dioxide levels in the atmosphere track the warming and cooling that's happened repeatedly over the last 400,000 years. If we look at carbon dioxide today, carbon dioxide levels today at 416 parts per million are way above the highest levels they've been for at least 400,000 years, and in fact, probably far above the highest levels they've been for a couple of million years. Now, some of these warm periods between ice ages were extremely warm in the past, warm enough, for example, that you had hippopotamuses living in Great Britain, just to give you an example. So the amount of greenhouse gas in the Earth's atmosphere today is way over 100 parts per million higher than it was at any time, any of these warm times in the Earth's recent past. And if we continue to burn fossil fuels at the rate that we've been burning them, by the end of the 21st century, we will probably have doubled the amount of carbon dioxide in the Earth's atmosphere relative to how much it has had over the last probably 500,000 to 1 million years. So climatologists talk about feedbacks, and in particular, they talk about positive feedbacks. A positive feedback is something that you have a cause, the cause leads to an effect, that effect amplifies the cause, which leads to even greater effect, which amplifies the cause even more, which leads to an even greater effect. So if you warm the climate of the Earth and you melt the sea ice around the North Pole, you expose more water. Water absorbs more energy from the sun than ice does. So the less ice you have, the more heat you absorb, the warmer the Earth's climate becomes, which melts even more ice, which leads to even more warming, which melts even more ice. So this is a good example of a positive feedback. There are lots of effects that occur from climate warming that tend to enhance, through positive feedbacks, additional warming. And one of the things that climatologists are worried about are thresholds. What's a threshold? Well, a threshold is a point where you reach, where you cause enough climate change that it triggers these positive feedbacks to kick in and accelerate the pace of climate change far beyond the rate at which it was changing previously. And so we worry about tipping points. We worry about reaching these triggers where we might start melting so much permafrost and releasing so much methane into the atmosphere, a very potent greenhouse gas, that temperatures increase much faster than we predicted initially. So why are we concerned about climate change? Why are we concerned about a warming climate? Well, mainly we're concerned about a warming climate because of the effects that climate warming will have on human civilization. We have built a civilization to match the climate conditions that have existed over the last 100 years. If those conditions change a lot, we're going to have to adapt. And adaptation is very expensive, both in money and in lives. For example, the climate of New York State, as it existed in the latter half of the 20th century, as the Earth warms, is going to change, and it's going to increasingly resemble the climate of more southern states. Now, if we get our greenhouse gas emissions under control and slow down the rate of climate change, we're not going to be able to stop climate from changing. It's already changing, and there's enough greenhouse gas in the atmosphere now that it's going to continue to change. It's really just a question of how much. So, you know, sort of the question now is, by the end of the 21st century, is New York going to have a climate similar to the present climate of Virginia, or is it going to have a climate similar to the present climate of Georgia? Now, Georgia is basically subtropical, so we're talking about upstate New York becoming essentially subtropical. Is New York City, which experienced on average about 2 days a year where temperatures got above 100 degrees in the late 20th century, by the end of the 21st century, is New York City going to be experiencing a week of over 100-degree days or a month of over 100-degree days? Now, if you've ever been in New York City when the temperature is over 90, you know how uncomfortable it is. But it's not just uncomfortable, it's dangerous, because if you are somebody who doesn't live in an air-conditioned apartment, or if you're elderly, or if you have health problems, these extreme high temperatures become deadly. And in fact, heat waves kill thousands and sometimes hundreds of thousands of people. So they're very, very dangerous and very concerning events. And they're heat waves disproportionately affect the poor and the elderly. Another impact of climate change is going to be shifting patterns of rainfall and expansion of the arid belts in the low latitudes to higher latitudes, and that's going to shift agricultural productivity away from some of the main population centers of the world. So in the United States, if we just focus on the United States, the American South and Southern Midwest is going to, and Southwest is going to become drier. And a lot of agricultural activity that now happens in these areas is going to become threatened. And the productive zones for agriculture are going to shift northward in the northern hemisphere. And this is a problem because, you know, we have farms in certain places, and if we have to move all that farming effort, that's going to be very expensive and very difficult to do. And it threatens our ability to produce the amount of food that we need to produce to feed a rising global population that's now approaching 8 billion people. If you want to demonstrate to someone that climate change is a very real threat, you need only look at this particular diagram here. This is a graph produced by Munich Re, which is a very, very large insurance company based in Europe. And what this graph shows is the number of natural disasters around the globe from 1980 to 2015. And the disasters are broken down by category. And the main point to notice here is that you have meteorological events, you have hydrological events, and you have climatological events in green and blue and orange. All of these types of disasters, tropical storms, thunderstorms, floods, landslides, droughts, heat waves, wildfires, these are all related to climate. The only category of natural disasters that's not related to climate are the red natural disasters, geophysical events, earthquakes, tsunamis, volcanoes. These don't pay any attention to climate. If you look at the graph, it's pretty clear that the number of global natural disasters has been increasing through the end of the 20th and into the 21st century. Natural disasters are becoming more common. What's particularly telling, though, is that if you just look at the geophysical disasters in red, they're not increasing. The disasters that are increasing are all of the things that are related to the Earth's atmosphere, related to climate. Right? So if the increase in natural disasters was just due to having more people living in harm's way, then you would expect to see a rise in disasters caused by geophysical events. But the fact that you don't is really, I think, it's kind of a controlled experiment in a way. The geophysical events are the control, and they're not increasing. But all of the climatological events are increasing, which basically shows us that as the Earth's climate warms up, as you have more energy in the atmosphere becomes more dangerous. And finally, one of the very important impacts of climate change is an acceleration in the rate of sea level rise. As you warm the atmosphere, you melt more glacial ice on land, and you return that water into the oceans. You also warm the water that's already in the oceans, which causes it to expand. It takes up more space. And both of these factors cause the sea level to rise around the world. And the rate at which sea level is rising has been accelerating. So in the early 20th century, it was rising at about a rate of 1 millimeter a year. The mid 20th century, about 2 millimeters a year. Currently, sea level is rising at over 3 millimeters per year, which translates to about a foot a century. And again, if we continue to dump carbon dioxide into the Earth's atmosphere, it's likely that we will continue to increase the pace of warming, and the rate of sea level rise will continue to accelerate. And this is a problem because a very significant proportion of global population lives close to sea level. And if you raise sea level, you will flood people's homes and businesses along the coastline. So if we take a local example, the New York City area, if we don't do anything to reduce the amount of greenhouse gas, fossil fuels that we burn and the emissions of carbon dioxide into the Earth's atmosphere. By 2050, global sea level will have risen enough to significantly flood or permanently flood significantly populated portions of the South Shore of Long Island, portions of the North Shore of Long Island, and parts of New Jersey. Now, equally troubling is the fact that as you bring sea level higher and higher, even the places that don't flood become increasingly prone to flooding during storm events. So New York City, for example, lower Manhattan, Hurricane Sandy did a very effective job of flooding large parts of lower Manhattan. Hurricane Sandy was considered to be a 100-year storm event, the kind of storm you would expect once every 100 years. But if you bring sea level up another foot, then the amount of flooding that was caused by Hurricane Sandy might become something that happens every 50 years, or even every 20 years, or maybe even every 10 years, depending on how high sea level becomes. All right, so you increase the frequency of storm flooding events as sea level rises. And this becomes a very expensive and a very dangerous problem. A lot of people lost their lives because of the flooding during Hurricane Sandy. And millions and millions and millions of dollars, billions of dollars, in fact, in insurance losses were incurred by the flooding that was a result of Hurricane Sandy. I hope from this you can better understand Greta's anger at the fact that the nations of the world are doing so little to address what is in many ways an existential threat to humanity's prosperity and well-being. We need to get away from burning fossil fuels as quickly as possible, and we need to transfer our energy economy to renewable sources of energy: solar, wind, hydro, geothermal, sources of energy that do not dump carbon into the Earth's atmosphere. Well, I hope you found that informative, and I hope you enjoy reading the book. And I look forward to discussing the book with some of you during the orientation sessions that will take place over the summer. Till then, stay safe.